At the very heart of quantum mechanics, there's this massive identity crisis. For centuries, we were pretty sure we knew what light was, and for that matter, what a particle was. But as we're about to see, nature had a pretty shocking surprise in store for us, one that forced us to completely rewrite the rules of reality itself. So let's shine a light on one of the greatest mysteries in all of physics.
So this was the big question, right? The one that kept physicists up at night. For years, all the evidence pointed in one direction. But then, this one stubborn experiment came along that just refused to play by the rules. It suggested something else entirely, something that, at the time, seemed just plain impossible. And for the longest time, the wave theory just worked. It was beautiful. It perfectly explained how light bends, how it splits into a rainbow, and how it interferes with itself. It gave us this really neat and tidy picture of the world. Or so we thought. But then, in the late 1800s, scientists stumbled onto something, a phenomenon that the wave theory couldn't just explain, it flat out contradicted it. And this wasn't some tiny little problem on the fringes. No, this was a full-blown crisis. Enter the photoelectric effect. Now I know, it sounds super technical, but the basic idea is actually pretty simple. You shine light on a piece of metal, and sometimes electrons pop right off. The mystery wasn't that it was happening, but how it was happening. The clues just weren't adding up. All right, so let's look at the scene of the crime. You've got this special metal plate inside of a vacuum tube. You shine a light on it, and you use a detector to see if any electrons get ejected. Super simple setup, right? But the results, well, they were about to turn physics completely on its head. Okay, so clue number one. At first, this seemed totally logical. The wave theory said a brighter light is a more powerful wave with more energy, so it should be able to knock more electrons out. And guess what? That's exactly what they saw. And yep, you can see it right here in the data. It's a perfectly straight line. You crank up the intensity of the light, you get more electrons, which means a higher current. So far, so good. The wave theory is looking great. Case closed? Not even close. And this is where the whole case for the wave theory just completely falls apart. Think about it. If a giant tsunami hits the coast, you'd expect it to throw debris much faster and farther than a tiny little ripple, right? Well, with light, it didn't matter how blindingly bright they made it. The electrons that got knocked off, they never came out any faster. Their maximum energy just stayed the same. You can see it right here. This stopping potential is basically a measure of the electron's max energy. It's how much of a headwind you need to apply to stop the fastest ones. And look, for 3 different light intensities, that stopping point, minus V0, is in the exact same spot. A brighter light gave them absolutely no extra energy. The wave theory had no answer for this. Okay, so if making the light brighter wasn't giving the electrons more oomph, what was? Well, it turns out the secret was the light's color, or more technically, its frequency. A low-frequency red light might not do anything at all, but a high-frequency UV light, it would send electrons flying out with incredible speed. And this graph just lays it all out plain as day. As you move to higher and higher frequencies, from nu 1 up to nu 3, you need a much stronger headwind, a bigger stopping potential to stop those electrons. That's direct proof that they're coming out with way more kinetic energy. The key was frequency, not intensity. So you can see it was a complete and total failure for the wave theory. It couldn't explain why energy was tied to frequency. It couldn't explain why, for any given metal, you had to hit a certain minimum threshold frequency before any electrons came out at all. And it couldn't explain why the electrons were ejected instantly. The old theory was officially dead in the water. And then, in 1905, along comes this young patent clerk. You might have heard of him, Albert Einstein. And he didn't even try to fix the old theory. No. He proposed something so wild, so out there, it sounded like science fiction. Einstein's idea was just mind-bending. He said, forget the wave. Think of light as a stream of tiny, discrete packets of energy. He called them quanta. Today we call them photons. So it's not a wave washing over the metal. It's more like a hail of tiny, invisible bullets. And from that single brilliant idea, he came up with this equation. It looks simple, but wow, it changed everything. It says that the maximum kinetic energy an electron can have is equal to the energy of one of those light bullets, the photon's energy, h nu, minus what you can think of as an exit fee the electron has to pay to escape the metal.
We call that the work function. So let's break that down, because it's actually pretty intuitive. It's a one-on-one deal. One photon hits one electron. The electron immediately uses some of that energy to pay the exit fee, the work function, just to break free from the metal's surface. And whatever energy is left over, that becomes its kinetic energy, how fast it's moving.
And boom, just like that, every single mystery was solved. Why does brighter light knock out more electrons? Well, brighter light is just more photons, so you get more one-on-one collisions. Why does the energy depend on frequency? Because the energy of a single photon, h nu, depends on frequency. What about that threshold? Easy. If a single photon doesn't have enough energy to pay the exit fee, the electron can't escape. And why is it instantaneous? Because it's a direct collision. It was a masterpiece of an explanation.
So, Einstein just proved that light, something everyone knew was a wave, could act like a particle. And that just blew the doors open to an even crazier question. You know, if nature has a thing for symmetry, could this be a two-way street?
I mean, just think about that for a second. Could things that we know are particles, an electron, a proton, heck, even a baseball, could they also have a secret life where they act like a wave?
Well, in 1924, a physicist named Louis de Broglie was brave enough to propose exactly that. He came up with this equation, the de Broglie relation. He suggested that every moving object, from an electron to a planet, has a wavelength lambda that's equal to Planck's constant h divided by its momentum p. It was a bridge between the particle world and the wave world.
Okay, but hold on. If that's true, why don't we see a baseball ripple through the air when a pitcher throws it? Well, it all just comes down to scale. If you do the math for a baseball, its wavelength is so ridiculously tiny, we're talking 10 to the minus 34 meters, it's completely impossible to measure. But an electron, its wavelength is tiny, sure, but it's on the same scale as an atom. It's big enough to be measured, and it's big enough to matter. And later experiments proved he was absolutely right. So, where does all this leave us? Well, it means our universe is just fundamentally weirder and honestly more incredible than we ever thought. It seems everything, absolutely everything, has this dual nature. This really ties the whole story together, doesn't it? On one side, you have light, radiation, which we thought was a wave, but the photoelectric effect proved it acts like a particle, a photon. On the other side, you have matter, particles like electrons, which de Broglie showed can act like a wave. It's not a contradiction. It's just two sides of the very same quantum coin. And that leaves us with one last really big question to chew on. If everything in the universe can be a wave one moment and a particle the next, depending on how we measure it, then what do those words even mean? Maybe particle and wave are just human labels we've put on a much deeper, much stranger quantum reality that we're all still trying to figure out. What do you think?